So today's topic is DC motor speed control system. So we can control the DC motor speed, especially that we by adjusting the speed excitation, you can adjust the DC motor speed control. So formula equations are DC motor speed is equal to 5Z and by 60 into P by A. So this is the equation for the DC motor. So in this case, 5 is a plus, Z is a conductor, ammeter conductor. So N is a speed. The P is a number of poles. P is a number of ammeter per part. So this is equation to calculate the DC motor voltage. So DC motor voltage is equal to the 5Z and by 60 into P by A. So EB is a back EMF, 5 is a plus, Z is a number of ammeter conductor, and the speed, P is a number of pole, and the A is a number of ammeter per part. So in this case, you can draw the equivalent diagram here. So this is for the speed, ammeter resistance RA. So we get the supply voltage. So we get the supply voltage, so current here, so some currents are flow through the field. So ISA here, the IA here. So I do that. So in this case, by adjusting the speed excitation current, you can adjust the flux. You can apply the flux and then according to this equation, we can adjust the speed. So this is the way that we control the DC motor speed. So by adjusting speed excitation current. Speed current. So DC motor speed can be controlled. DC motor speed can be controlled. So this is for the speed control method. So normally electrically we control the speed. By the adjusting the speed excitation current, we can control the DC motor speed. But in the meantime, we also utilize the electronic control system. So we use the silicon control rectifier system to control the DC motor speed. So in this case, I will draw the control diagram of the SCR system. So SCR system control system, how we utilize it? Normally, we use the AC to DC conversion. So AC is a 3-phase. So this is a 3-phase AC. So this 3-phase AC is considered change to the DC by the SCR. So this is usually the SCR bridge. So we need 6 SCR bridge together. So SCR bridge are connected like this. So here we use the supply. So this is connected to the motor. So this is the motor load. So we connect like this. So this one we connected to heat like this. So in this case, we use the SCR. So SCR, to fire and get you get control. So this is the SCR. SCR, this is the case. So by controlling the case firing and gate, we can control the conduction of the SCR. So this is the SCR control system. So this becomes a silicon SCR silicon control rectifier. So we can control the silicon control rectifier. We utilize for the AC motor speed control. And also we can utilize also for the DC motor speed control. So then by controlling the SCR, so this becomes an SCR case here. So input will be the sinusoidal signal. But output is depending on the SCR case firing signal. So we can control the SCR signal like this. So this began as a firing engine. Firing engine. So by controlling the SCR signal, we can control the firing engine. So firing engine, by controlling the firing engine, we can control the conduction. So the conduction is we can control the speed of the SCR. So this way is how we can write down the block diagram. A block diagram all of this control. There will be that this is the input. So this is the SCR unit. So this SCR unit is connected to the output body. So output body is connected to the motor. So the output body supplies the motor. So motor rotates. So motor rotates is produce the speed. So when the speed is produced, we use a sensor. So we send the speed of the motor. Speed of the motor, and this one will be the connected to the speed output. So this is sensor will use a tachometer. Tachometer. So we use a tachometer. So this one uses a tachometer, also triangular. The transducer is used as a combination. So this is compared with the reference signal. So reference signal any error is fed to the cadence circuit. So the cadence circuit drive the SCR. So this is for the typical speed control system. So this is the block diagram of the SCR control model. Block diagram. Of SCR control model. So we use the block diagram of SCR control model. So when we supply the supplying body to the SCR unit, then the SCR units are produced depending on the KPI, and then it produces the output PO. So this output PO drive the motor. So the motor speed is set by the tachometer sensor, and then this one is compared with the reference, and then any error is supplied to the cadence circuit. So this is the block diagram of the SCR control model. This is the part. So this is SCR drive system. This is a switching circuit. So switching circuits are produced as DC voltage, but this DC voltage is not pure DC. Because of this switching, DC voltage with the fast-rated DC. Fast-rated DC with this DC voltage will be like it. SCR unit is produced as fast-rated DC like it. So this is a fast-rated DC voltage. So this DC voltage one disadvantage is that this DC voltage can this includes repair. Repair means produced by the high frequency switching. So high frequency switching, they produce a repair. So this repair is a disadvantage can produce a hidden effect. So hidden effect on the repair. So hidden effect of repair means that this SCR unit is producing the fast-rated DC. So this is a repair. So repair is disadvantage can produce a hidden effect. So repair produces a hidden, and also this repairs are produce a harmonics. Harmonics are the frequency higher than the fundamental. So those harmonics need to be eliminated by the fader. Need to be eliminated. By fader. And also this harmonic also produces a vibration. So because of this kind of vibration, we also need to use the appropriate vibrations absorber. So those are important for the DC machine system. Vibrations so because of this one these repairs are they produced by the high frequency switching circuit. So these repairs are produced by high frequency switching circuit. So high frequency switching circuit can be the PWM device. So PWM drive means by switching we can form as a sideways. So this is for the sideways is a form of this kind of switching. So this is the bidirectional we can form a sideways. So this is we call the PWM system. PWM system means PWM means power with modulated system. Power with modulation. So this PWM systems are produces repair. So these repairs are functioning. It can cause the heating, harmony, and the vibration can happen because of this repair. So these repairs are need to be delay the machine. So this repairs are also disadvantage is delay the machine. And also that you can also delay the insulation. So those are the high frequency switching circuit. So in this case we use lights as normally we control the system on speed. One control means the speed control, speed current can be controlled. And the modern control system instead we use the SCR unit. So SCR units are produced as variable frequency waveform. So those waveforms are that they drive the machine. So but the disadvantage of the SCR system is it can produce a repair. Repairs are produce the heating, harmony, and vibration. So that due to this effect that it can delay the machine and delay the insulation. So this is for the speed control, electronic speed control system. So apart from this kind of the electronic speed control system, in the former case are very heavy duty machines. We also utilize all the other kind of the system, speed control system. So AC motor speed control, we can change the supply frequency, we can control the AC motor speed. And DC motor speed control is that there are three major methods. Shunt current. So shunt current I already given you. Shunt current we can control the current flow in the shunt or the armature current. You can also control the armature current and the one unit control system. So one unit control system means that the motor is driven by the generator, and then this DC generators they drive another motor. So this motor, by adjusting the motor, by this way we can adjust the motor, armature current, as well as the motor the field excitation current. So then we can control the motor field. So this is both the armature current and the field current control is a one unit control system. So another two kinds of the control is straight control system. Shunt current can be controlled or the armature current control. So by controlling the armature current and shunt current, the third system will be a one unit control system. So now I give you the speed control method for the DC motor. For the control system, normally the AC current is equivalent to the DC. And this DC is respect to the PWM system. Power and modulated control. So this modulated control system, they form the AC. And that is connected to the motor. So this is for the AC motor speed control system. So by adjusting the partial modulator to AM frequency, also depending on the switching frequency, so by this way we can control the AC motor speed. And shunt control is that we adjust the shunt current flow into the motor shunt speed, and then we can control armature control. We can adjust the current flow into the armature winding, and then we can control. And then one unit system is that we use the motor generator set. So now I give you the one unit system. So one unit system is that this is an input with the three-phase motor. Three-phase motor is connected to the couple, and then you can use the generator here. So the generator is the drive motor winding. So this is for the DC motor. So DC motor speed. So this is the terminal voltage VDS given. So generator terminal is connected to the motor by this way, and then the generator P excitation. So P excitation is we can also utilize for the exciter. So this is the excitation part. So excitation bus bar is the excitation bus bar. What we use is this motor is also used as this small exciter motor. So this small exciter is connected to the excitation bus bar. So this is positive and negative. So this is the excitation is applied to the DC generator. So DC generator armature voltage supplies the motor armature. In the meantime, this excitation bus bar is also connected to the P winding of the DC motor. So by this we can adjust the motor current. So this is the generator current can be adjusted by using the adjuster. So we adjust the P excitation. So we adjust the P excitation so the generator voltage can be adjusted. So generator voltage adjust, so the adjust generator voltage supplies the DC motor, and there's a DC motor speed will be adjust. So that we can adjust the excitation of the generator. So that this is why this is a one unit system. One unit system produces the generator. Generator is connected to the P excitation. So P excitation is connected to the bus line connected to the exciter. So exciter voltage we can adjust the generator excitation so that we can adjust the generator voltage. So the generator voltage, the variance generator voltage applied to the DC motor, so motor speed can be changed. This is we use the one unit control system. So this is the one unit tool. So motor speed too high, so we have to reduce the excitation, and motor speed is too low, we have to increase the excitation. So that this motor speed is set by the sensor, and then we can adjust the excitation. So this is the way that we adjust. So one unit system is a very widely used in the very high power straight system. We use a one unit system. This is for the one unit system. So only the P excitation, we have to follow this equation. EV is equal to 5Z and my 60 to P by A. So by adjusting this 5Z brings the proportional to the P excitation current. So by adjusting the P excitation current, the flux can be adjusted and also the motor speed can be adjusted. So this is the one way of the P control system. And the armature control system is by adjusting the P rheostat, we can produce the generator voltage. So generator voltage varies depending on the P rheostat setting. So this generator voltage also develop the current set into the DC motor. So this is DC motor armature. You'll see the variance current and the motor speed can be regulated. So in this case, the four of DC motor armature control, current control, where to use as equation. So this equation is P is equal to K phi into IA. So this is equation. So this is because the P is a top. K is a constant, phi is a flux, and IA is an armature current. So armature current in the ampere, T is a torque with a Newton meter, and flux unit with a watt. So T is equal to K phi IA. So this is for the torque equation for the DC motor. Also the K, also you can calculate. So K is this is a KT, KT phi IA. KT can also be calculated. KT is a constant. The constant can be calculated by this formula. P is divided by 2 pi A. So this is a KT. So in this case, KT is P is a number of poles, and Z is a number of armature, number of polarization armature, number of conductor. in armature. And also A is an armature pair part. Is a number of armature pair part. So that this is the equation to calculate KD. So T dot equation is equal to KD phi I A. So the KD can be calculated PZ divided by 2 by A equation. And also the E, generator voltage and E is the back EMF or generator voltage is equal to the KE phi in the N. So that in this case, EG is the generator voltage. So phi is a plus and N is a speed. So we also need to calculate the KE. So KE for formula can be calculated the equation here. KE is also constant. So this is the KE which can be calculated by this formula. KE is equal to PZ divided by 60A. So then P is the number of poles, Z is the armature number of conductor. And so 60 is a constant and A is the number of armature per part. So by this way, molar torque equation can be driven by the equation. This equation to calculate the molar torque. So that can be the T is equal to K phi and then BT divided by RE minus KE KT phi square and divided by RE. So this is the equation to calculate the molar torque. So in this case, this molar torque means that KT and the KE are already given. So BD is the terminal voltage, RE is the armature resistance. So this equation, so the equation to calculate the molar torque. Equation to calculate the molar torque can be the formula T is equal to KD phi BD by RE minus KE KD phi square and divided by RE. So this equation is the molar torque. So in this case, you can see that it can affect the motor armature current. So the BD divided by RE. BD is the motor armature resistance here. RE is the DC motor winding armature resistance. So that we can change the motor speed. So motor speed is depending on the motor supply voltage. So this variance supply voltage is produced by the DC generator, and also this DC generator variance voltage is depending on the PVO setting. So by this is you can adjust the motor speed. So the basic formula to calculate the motor speed is T is equal to KD phi BD by RE minus KE KD phi square and divided by RE. So this equation is utilized to control the motor speed by the one unit system. Okay, this problem, the 4 poles waveform armature operated in the field of flux of 0.01 weber in one with the 360 armature conductor. So the determine the expression of torque as a function of T is a BD 250 volt and the RE 0.01 ohm. So this is that we have to write the torque as a function of the speed. So here you see the torque. Torque T is equal to KD phi BD by RE minus KE KD phi square and divided by RE. So it is the relation between the torque and the speed. So T is the torque and the speed. So this equations are called the left hand side the T. So this T is depending on the speed. So this is the torque is the function of speed. So we have to write down this equation. So firstly we write down the equation T is equal to KD phi BD by RE minus KE KD phi square and by RE. So this is we can write T is equal to KT phi BD by RE minus KE KT phi square and divided by RE. So this is the torque as a function of the speed. So after the 6 months, you have to find the parameter. So you have to find the value of the KT, you have to find the KE, and find plus BD, you have to substitute. So firstly, you have to calculate the KT formula. KT formula is given the PZ divided by 2 by A. So this is the equation given. So we calculate the KT. KT is equal to PZ divided by 2 by A. So P is the number of poles. So in the problem already given, this is a 4 poles are waveform. So the P is equal to 4 already given. And number of armature we already given the 360, and so A is the number of armature per part. So there are two formulas to calculate the A. A is equal to 2 multiply N for the left winding, 2 and A is equal to 3 multiply N for the left winding, and 2 multiply N for the right winding. So left winding is A is equal to 3 multiply N. So right winding is A is equal to 2 multiply N. So P is the number of 4, A is the plus number. For the simplest N equal to 1, duplex N equal to 2. So if this problem is just not given the N is the plus number, so we can assume that the simplest. So then assume simplest. So therefore the N is equal to 1. So the simplest way. So A is equal to 2 multiply N. So 2 multiply 1, so A is equal to 2. So now we can substitute here. So KD formula we substitute. Number of 4 is 4. And number of armature formula 360 to find the 3.1416 and divide by 2. So by solving this one, you got the 114.5. This is the KD. And similarly, you can also calculate the KE. KE is equal to PZ divided by 68. So we substitute. Number of points is 4. Go to 360 divided by 60. And number of armature per is 2. By solving this one, KE we got the 12. So we got the KE and the KD value. And then we now substitute here. T is equal to KD 5 BD RA minus KE KD 5 and RA. So this one we can substitute. So we got a key. So KD value, you substitute the 114.5. Multiply the plus. So plus is already given the 0.01 river. So 0.01. Multiply terminal with BD. So it's given a 250 volt. Divided by armature resistance R is 0.1. Minus, and the KE value is a 12. Multiply KD value already given as a 114.5. Multiply plus square is a 0.1 square. 0.01 square. Multiply 3 we don't know the 3. And divided by the armature resistance 0.1. So by solving this one, what you call is T is equal to 2800 minus 130 N. We got. So T is 2800 minus 330 N. So this is for the we can represent the torque in the term of speed. Okay, another thing is that we also need to calculate for the no load speed. So no load solution, there is a zero torque. Zero torque is a no load speed. So from this equation, when the machine running without load, what will be the speed we can calculate? So we can calculate for the no load speed. No load solution of T equal to 0. So the 0 equal to 2800 minus 130 N. This is 1.38 N. So 2800 minus 1.38 N. Then you can calculate N. So 1.38 N is equal to 2800. So N equal to 2800 divided by 1.38. So the molar load speed will be 2070 RPM. So by this you can write the motor load speed as well as a torque and speed relationship. For the torque and speed relationship, so that this equation we got is a T is equal to KT 5 BD by I minus KE KD 5 squared and divided by I. So this equation we got. So that from this equation we can draw the graph. So this graph will be a no load speed condition. So torque and speed we can calculate. So this is for the quantification with the torque. And for the issue with the speed. So the higher the speed, the lower the torque. So this is we can this graph we go like this. So this is equation will be the for example T is equal to KT 5 BD by RA minus KE KT 5 square and divided by RA. So in this case gradient. So this is a gradient. So gradient will be minus Ke Kt pi square by Re. So this is a gradient. So what are the three gradients we can calculate by this equation? So this is the top three characteristics for the DC model. Why we need to do this characteristic is that the system characteristic and the model characteristic need to be matched. So system and dry system and the model, their characteristics need to be matched. For example, one system which is the constant torque collision. So this is P and the torque. So this is the constant torque. And another system where we use torque and speed is changing like this. So this is especially for the series model. So this is for the constant torque fluctuation. We can also write, and this is vertical speed, and this is torque. So we will change it like this. So this is for the series model. So all the models are called different characteristics. So when we are using the model to the particular drive system, the system characteristic and the model characteristic need to be matched. So regarding this discussion, we will solve the one problem. So this problem you will see that is given the system characteristic and the model characteristic, and then we need to match. We need to match so that at the matching point is the equilibrium point. Equilibrium point is at this point the model should be operated. So this is for this model system. The model characteristic is 2860 minus 1 by 3 n. So this is for the model characteristic. And the loads are load 1 characteristic T is equal to the 50 plus 1 by 2 by n. The load 2 is T is equal to 50 plus 1 by 625 into 10 power minus 4 n squared. So this is this model is running the two kind of loads. So we need to calculate the model equilibrium speed for the K. So in this case, so to mention the thing is that you have to solve this two equations. So firstly we have to try the model and the load. Model and the load. T is equal to 50 plus 1 by 2 pi n. So this is that. So we saw the equation. So so the two make the equilibrium. Model torque must be the load torque. So model torque must be equal to load torque. So this is the equilibrium condition. Equilibrium condition means not too fast or not too slow. So in this case, model torque must be equal to load torque. So that we write the equation. Model torque equation is T is equal to 2860 minus 1 by 3 n. So we substitute 2860 minus 1 by 3 n. So load torque equation is 50 plus 1 by 2 by n. 50 plus 1 by 2 by n. So this equation we solve. So this we can calculate the equation. So that way 2860 minus 50. So 1 by 3 n plus 1 by 2 by n. So we add 1 by 3 and then 1 by 2 pi and we go so that way we just 2 points. So 1 by 3 8, 1 by 2 pi. So 3, so this is 2 pi 6 3 n. So 2 pi 6 3 n. So then, so that 2860. So then you got the n. So when the model 3 we calculate. So then we get 1900 RPM. So by this way you can calculate for the model 3. And second equation is we have to measure the model and the load. T equal to 50 plus 0.625 into 10 power minus 4 n squared. So we run the model. So model and the load. So T is equal to 50 plus 0.625 into 10 power minus 4 n squared. So this model is running at this load. So in this case, we also need to equate model torque and the load torque are equal. So model torque equal to load torque. So then we make the equation. So molar torque is equal to the 2860 minus 1.38 N. The load torque is equal to the 50 plus 0.625 into 10 bar minus 4 N squared. Okay, we write, so this one is changing the top. So today's topic is DC motor speed control system. So we can control the DC motor speed, especially that we by adjusting the speed excitation, you can adjust the DC motor speed control. So first the equations are DC motor speed is equal to 5Z N by 60 into P by A. So this is the equation for the DC motor. So in this case, 5 is a plus, Z is a conductor, ammeter conductor. So N is a speed. The P is a number of poles. P is a number of ammeter per path. So this is equation to calculate the DC motor voltage. So DC motor voltage equal to the 5Z and by 60 into P by A. So EB is a back EMF, 5 is a plus, Z is a number of ammeter conductor, and the speed, P is a number of 4, and the A is a number of ammeter per path. So in this case, you can draw the equivalent diagram here. So this is for the speed. I'm going to say RA. So we get the supply voltage. So we get the supply voltage. So current here, so some current are flowing to the feed. So ISA here, the IA here. So I do that. So in this case, by adjusting the feed excitation current, you can adjust the flux. You can apply the flux, and then according to this equation, we can adjust the speed. So this is the way that we control the DC motor speed. So by adjusting feed excitation current. Feed current. So DC motor speed can be controlled. DC motor speed can be controlled.